Buckle up, everyone, because today we are taking a deep dive into quantum mechanics.
Oh, yeah, it's going to be a wild ride.
You guys sent in some seriously fascinating excerpts from a textbook on quantum mechanics.
Dense stuff.
Definitely dense, but
Super interesting, though.
yeah.
I mean, it really makes you question everything you thought you knew about the universe.
Well, let's jump right into some of the weirdness.
Okay.
So the textbook starts by talking about how the quantum world is chunky.
Yeah.
Like instead of energy levels being continuous, they exist in these discrete steps.
Yeah, like a staircase.
Right. And they actually talk about experiments that demonstrate this discreteness.
Like the one where they were able to resolve individual energy states of hydrogen atoms.
Oh, wow.
Yeah, from N63 all the way up to N72.
It's amazing.
Really precise measurements that allow us to see those quantized energy levels.
It's like zooming in on reality and seeing that it's made of pixels.
Kind of, yeah. It's wild.
Then there's this whole wave-particle duality thing.
Oh, yeah. One of the biggest mysteries in quantum mechanics.
I mean, the textbook talks about electrons exhibiting diffraction and interference patterns just like light waves do.
It's like, how can a particle act like a wave?
Right.
It's mind-boggling. And the double slit experiment really highlights this.
Oh, yeah, that's a classic.
Even when you fire single electrons at those slits, over time, they build up that interference pattern as if each electron went through both slits at the same time.
It's like the electron knows about both paths, even though it's just one particle.
It really does.
It's enough to make your head spin, and then on top of that, we have to deal with probability.
Right.
Instead of predicting definite outcomes, quantum mechanics is all about the probabilities of different events happening.
Yeah, it's like the universe is playing dice.
And that's where the math comes in, right?
Oh, yeah.
The textbook dives into the mathematical framework of quantum mechanics.
Using things like linear vector spaces, operators, eigenvalues, all that fun stuff.
I have to admit, that's where I start to get a little lost.
It can be pretty abstract, for sure.
Is there any way we can try to unpack some of those mathematical ideas without getting too bogged down in the equations?
Sure. So imagine you have a musical instrument, right?
Yep.
Each note you can play represents a specific quantum state.
All right.
Now picture a musician playing a chord.
Yeah.
That chord, that combination of notes that's like a quantum state, that's a blend of those individual notes just like a quantum state, can be a superposition of different possibilities.
I see. So the chord is like a superposition of different notes.
Exactly. And then we can think about operators.
Okay.
They're like actions you can perform on that musical chord. You can shift the whole chord up or down in pitch or change its volume.
So each action is like an operator.
Yep. And then the eigenvalues come in as those specific values associated with those transformations, like shifting the chord up by a whole step. That specific step represents an eigenvalue.
So the operator changes the chord, and the eigenvalue is the specific amount of change.
You got it.
Okay, that's starting to make a bit more sense. So it seems like quantum mechanics isn't about knowing exactly which note is being played.
Right.
It's more about understanding the probabilities of hearing certain notes within that chord.
Yeah, it's not about certainty, but about the likelihood of observing a particular value when we make a measurement.
So we've got this crazy quantum world where energy levels are like steps on a staircase, particles act like waves, and probabilities rule the game.
That's quantum mechanics for you.
But how do we actually study and manipulate these quantum states?
Well, that's where concepts like state preparation and state determination come in.
Okay, tell me more about that.
State preparation is all about setting up a quantum system in a very precise way so that we have a good idea of what the probabilities of different outcomes will be when we make a measurement.
So it's like carefully tuning that musical instrument before you start playing.
Exactly. And then state determination is like listening to the music and trying to figure out what notes are being played, or in the quantum world, what state the system is in based on the measurements we make.
So we set up the experiment with precision and then use the results to try to decode the quantum secrets.
Precisely. And then the textbook also talks about composite systems.
Composite system.
Yeah, systems made up of multiple particles,
Okay.
which adds another layer of complexity.
How so?
Well, because now we have to consider how the state of one particle might be linked to the state of another, even if they're separated by a large distance.
Now that sounds like we're really heading into some mind-bending territory.
Oh yeah, we're just getting started.
You mentioned that these composite systems introduce something called correlations between particles. Can you elaborate on that a bit more?
Sure. It's like these particles are communicating with each other in a way that goes beyond our classical understanding of space and time.
So like if we measure the state of one particle, we instantly know something about the state of the other, even if they're light years apart.
Exactly. It's one of those bizarre and fascinating aspects of quantum mechanics.
Definitely a whole new level of weirdness.
For sure. And the textbook actually gives some really interesting examples that illustrate these concepts.
Oh, yeah, like the spin recombination experiment.
Right. And then there's tunneling, where particles can pass through barriers even if they don't have enough energy to overcome them.
Yeah, those both really caught my attention.
They're both great examples of how quantum mechanics challenges our classical intuition. The spin recombination experiment in particular demonstrates the mind-boggling concept of superposition.
Superposition. So that's where a particle can be in multiple states simultaneously, right?
Yeah, like it can be in two places at once or have two opposite spins at the same time.
It's like flipping a coin and it landing on both heads and tails at the same time.
That's a good analogy.
And what about tunneling? The textbook talks about particles passing through barriers, even if they don't have enough energy to go over them.
Yeah, it's like they're teleporting through the barrier.
It's like rolling a ball up a hill.
Uh-huh.
And even if it doesn't have enough energy to reach the top, it somehow tunnels straight through the hill.
It really does defy our classical understanding of how things should work.
All right, I am officially blown away, and we haven't even touched on the big one.
The measurement problem.
The measurement problem, the textbook dives into that too, bringing up the role of the observer and the different interpretations of what's actually happening when we make a measurement in the quantum world.
Yeah, the measurement problem is one of the most perplexing and debated aspects of quantum mechanics. It seems like the very act of observing a quantum system can influence its behavior, forcing it to choose a specific outcome from a range of possibilities.
So does that mean our consciousness, our act of observing, is somehow shaping reality?
That's a question that has puzzled physicists and philosophers for decades.
It's a big one, and I'm dying to hear more about the different interpretations that try to tackle this problem.
Well, let's take a deep breath first.
Yeah, good idea.
That's a lot to take in.
This quantum world is definitely a wild ride.
It is, but it's a fascinating ride, and we're just getting started.
Yeah, it really does make you wonder about the nature of reality, doesn't it? It's like suddenly the universe became a lot less predictable.
And a lot more mysterious.
Yeah, but that sense of mystery is also what makes it so fascinating.
For sure.
Especially when you start thinking about the measurement problem.
Yes, the measurement problem.
It's like the universe is playing hide and seek with us.
How so?
Like it has all these possibilities hidden away,
Yeah.
but it only shows us one specific outcome when we decide to look.
Yeah, it's like the act of observation somehow influences what we see.
And that's why we have so many different interpretations of quantum mechanics, right?
Right. Each one trying to make sense of this bizarre behavior.
It's like we've stumbled upon a giant cosmic puzzle.
And we're trying to find the pieces that fit together.
So tell me about some of these different interpretations.
Okay, let's start with the Copenhagen interpretation.
Okay.
One of the most famous ones.
This was developed by Niels Bohr and Werner Heisenberg, right?
That's right, some of the pioneers of quantum mechanics.
So what's their take on the measurement problem?
Well, the Copenhagen interpretation says that a quantum system exists in a superposition of states,
Meaning?
meaning it's in all those possible states at the same time
Okay.
until a measurement is made.
And then what happens?
Then the wave function collapses, and the system chooses one definite state.
So the act of measurement forces the system to make a decision.
Kind of, but it was still a bit of a mystery what actually causes that collapse and what role the observer really plays.
Yeah, so the Copenhagen interpretation doesn't really explain the why behind it all.
Not exactly. It's more focused on the practical aspects of making predictions and interpreting results.
Okay, so it's like they're saying, here's what we observe, and here's how we can calculate the probabilities, but don't ask us about the deeper meaning.
Yeah, something like that. But it's important to remember that this interpretation was hugely successful in the early days of quantum mechanics.
Right. It provided a framework for understanding all those weird experimental results.
Exactly.
But I imagine other physicists weren't content to just leave those why questions unanswered.
Oh, of course not. There were plenty of other interpretations that tried to dig deeper.
Like what?
One of the most mind-boggling is the many worlds interpretation.
This is the one with parallel universes, right?
That's the one that was proposed by Hugh Everett III.
So instead of the wave function collapsing, the many worlds interpretation says that all possible outcomes actually happen.
Yes, but in different branching universes.
So every time we make a measurement, a new universe is created for each possible outcome.
It's a pretty radical idea.
Infinite universes.
Potentially.
But it does get rid of that whole wave function collapse issue.
Yeah, and it takes the mystery out of the observer's role.
So instead of one reality that's constantly changing based on our observations,
We have countless parallel realities playing out simultaneously.
wow, okay, that's a lot to process. Are there any other interpretations that try to address the measurement problem without resorting to infinite universes?
Sure, there's the de Broglie-Bohm theory,
Okay.
sometimes called the pilot wave theory.
And what does that one say?
This one suggests that there are hidden variables that guide the behavior of quantum particles even when we're not looking at them.
So there's like a secret set of instructions that we can't see.
You could say that.
So even though we see randomness in the quantum world,
Everything is actually predetermined by these hidden variables.
it's a very different picture than the probabilistic view.
It is, and it's important to remember that each interpretation has its own strengths and weaknesses.
Yeah.
And there's no one definitive answer to the measurement problem.
It's still a mystery.
A mystery that physicists are still actively debating and researching.
It's like opening a Pandora's box of philosophical questions.
Yeah, it really makes you think about what reality actually is.
And we haven't even talked about the implications of quantum mechanics for the universe as a whole.
Oh yeah, that's a whole other can of worms.
I mean, if these strange quantum effects are happening at the smallest scales, what does that mean for the cosmos on a grand scale?
It's a fascinating question, and one that we should definitely explore.
Okay, let's do it. I feel like we've only just dipped our toes into this whole quantum ocean.
It's a vast ocean for sure.
And there's so much more to explore.
Oh, absolutely. The implications of quantum mechanics go way beyond just the behavior of individual particles.
So what happens when we start thinking about these quantum effects on a larger scale, like the universe as a whole?
Well, things get really interesting.
Like how?
We've been talking about entanglement, this spooky connection between particles, even when they're separated by huge distances.
Right, like they're sharing some secret language that we can't decipher.
And some physicists believe that this interconnectedness might actually extend to the entire universe.
The entire universe?
Yeah, think about the early universe just after the Big Bang.
Okay.
It was this incredibly dense, hot soup of particles.
Right.
And some physicists speculate that everything was in this highly entangled state back then.
Like a cosmic quantum web connecting everything.
Exactly, and some even suggest that those primordial entanglements might still exist today, like echoes from the Big Bang.
So those spooky connections we see in the quantum world.
Could be remnants of those early universe entanglements.
Wow, that's a mind-blowing thought. It really challenges our ideas about space and time.
It does. If everything was once entangled at the Big Bang, it makes you wonder if anything is truly isolated in the universe.
It's like we're all part of this giant cosmic dance.
And then there's the question of what quantum mechanics might tell us about some of the biggest mysteries in cosmology,
Like what?
like dark matter and dark energy.
Ah, yes. The invisible forces that shape the universe.
And we still don't know what they are.
So how could quantum mechanics help us understand them?
Well, some physicists believe that the quantum vacuum might hold some clues.
The quantum vacuum.
Yeah, it's this seemingly empty space that's actually full of virtual particles popping in and out of existence.
Virtual particles, like particles that aren't really there but still have an effect?
Exactly. They're a consequence of the uncertainty principle, which allows for these fluctuations in energy over very short periods of time.
Okay, so empty space isn't really empty at all.
Nope. It's a seething cauldron of quantum activity.
And how does that tie into dark matter and dark energy?
Well, some physicists think that these virtual particles might contribute to the energy density of the vacuum,
Okay.
and that energy density could be related to dark energy.
So the quantum vacuum is like this invisible engine driving the expansion of the universe.
It's one possibility that's being explored.
Wow.
The point is that quantum mechanics is making us rethink our assumptions about reality on all scales.
It's like every time we think we're getting a grip on things, quantum mechanics throws us another curveball.
But that's what makes it so exciting. It's a constantly evolving field with so much left to discover.
And it's already leading to some incredible new technologies like quantum computing.
Oh yeah, quantum computing is going to revolutionize the way we process information.
And there's also quantum cryptography, which could lead to unbreakable codes.
The possibilities are endless.
It feels like we're on the verge of a quantum revolution.
I think we are, and it's going to change the world as we know it.
Well, this deep dive has definitely left me feeling inspired and eager to learn more about this amazing quantum world.
Me too. There's still so much to explore and understand.
So to our listeners out there, keep that curiosity alive. Keep asking those big questions and never stop exploring the mysteries of quantum mechanics.
Because who knows what incredible discoveries await you on your own quantum journey.
Thanks for joining us on this deep dive into quantum mechanics. We'll see you next time.
Bye, everyone.